A fully loaded semi-truck rolling down a mountain pass weighs up to 80,000 pounds. That is roughly the same as stacking 14 full-grown elephants on top of each other and pointing them downhill at 60 miles per hour. And the engine pulling all of that weight will never, not once, under any circumstances, spin past 2,100 RPM. A sports car engine hits that number just sitting in a parking lot. Your lawnmower gets there. So why does one of the most powerful engines on American roads run at what sounds like barely above idle? The answer has nothing to do with laziness in the engineering department. It has everything to do with physics, economics, and a set of engineering decisions that took decades to get exactly right. To understand this, you need to forget everything you think you know about how engine power works, because the intuition most people carry around is completely backwards when it comes to diesel. Most people assume that higher revolutions per minute means more power. In a gasoline engine, that is mostly true. Those engines are built to rev and they make their peak power high up in the rev range, which is why a sports car screams when you floor it. But diesel engines, the kind sitting under the hood of every semi-truck on every interstate in this country, are built on an entirely different philosophy. They are not designed to spin fast. They are designed to push hard. The technical term for that pushing force is torque. And a modern semi-truck diesel engine produces somewhere between 1,500 and 2,050 pound-feet of torque. To put that in perspective, a typical V8 pickup truck makes around 400. A Ferrari makes less than 600. A Class 8 diesel makes more than 3 times that, and it delivers almost all of it at extremely low revolutions per minute, sometimes as low as 1,000 to 1,200 revolutions per minute. That is the core of the whole story. These engines don't need to rev high because they already have everything they need right down at the bottom of the range. But why? Why does a diesel engine behave so differently from a gasoline engine in the first place? It comes down to combustion. A gasoline engine uses spark plugs to ignite a relatively thin mixture of fuel and air. The explosion is sharp and fast, which suits a high-revving design. A diesel engine does something fundamentally different. It compresses air so tightly, at compression ratios from 14 to 1 up to 25 to 1, compared to compression ratios of 8 to 1 to 12 to 1 in most gasoline engines, that the air itself gets hot enough to ignite the fuel the moment it is injected. No spark is needed. That extreme compression is what generates the enormous low-end torque. And extreme compression takes time. Not much time, but enough that pushing the engine to spin faster and faster starts working against itself. Above a certain number of revolutions per minute, the combustion cycle cannot complete properly. Efficiency collapses, power drops. The engine literally fights itself. So, the 2,100 revolutions per minute ceiling is not a limitation. It is the engine operating exactly where it was designed to operate. Now here is where it gets interesting, and where most people have no idea what is actually happening inside that cab when a driver is working a long haul. Trucking is not about speed, it is about fuel, and fuel is money. A commercial carrier running a fleet of 50 trucks across the country lives and dies by fuel economy measured in fractions of a mile per gallon. At highway speeds, a semi gets somewhere between 5 and 8 miles per gallon, depending on load, terrain, aerodynamics, and driving behavior. Every tenth of a mile per gallon improvement across a fleet of that size translates to tens of thousands of dollars per year. This economic reality shapes everything about how diesel engines are tuned and governed. When a diesel engine runs at its most efficient revolutions per minute, typically between 1,200 and 1,500 revolutions per minute for most modern engines, it burns the least fuel per unit of work produced. Engineers call this the sweet spot, and the entire drivetrain of a modern semi is designed around keeping the engine in that zone as much as possible. The transmission, the gear ratios, the axle ratios, the tire sizes, everything is calibrated so that at normal highway cruise speed, the engine is turning slowly, working efficiently, and burning as little fuel as possible. Pushing past 2,100 revolutions per minute would shatter that efficiency entirely. Fuel consumption would spike. The engine would be working harder to produce less useful output. For a driver running 600 miles a day, the cost would be immediate and measurable. But there is a second reason the revolutions per minute ceiling exists, one that matters just as much as fuel economy, and that is durability. These engines are not replaced like car engines. A well-maintained diesel in a commercial truck is expected to run for 600,000 to over 1 million miles before a major overhaul. Let that number sink in. 1 million miles. That is roughly 40 years of average American driving, crammed into the working life of a single engine. Achieving that kind of longevity requires keeping mechanical stress as low as possible for as long as possible. Every revolution of the engine creates wear. Pistons move up and down, bearing surfaces contact each other. Valves open and close. At 2,000 revolutions per minute, a 6-cylinder diesel is completing roughly 6,000 power strokes per minute. The forces involved are enormous. The higher the revolutions per minute, the faster those components wear, the more heat is generated, and the more stress is placed on every seal, bearing, and fastener in the engine. Running a diesel at sustained high revolutions per minute would shorten its life from 1 million miles to something far, far shorter, and in commercial trucking, a catastrophic engine failure in the middle of Nebraska is not an inconvenience, it is a financial disaster. The 2,100 revolutions per minute governor is partly a mechanical protection system. It is the engine manufacturer saying, "We will not allow this engine to destroy itself in the service of a driver who wants to go a little faster." And speaking of governors, yes, the RPM limit is enforced electronically. Modern diesel engines are managed by a sophisticated engine control unit, the ECU, that monitors dozens of parameters simultaneously. RPM, fuel injection timing, boost pressure from the turbocharger, exhaust temperature, coolant temperature, and more. The ECU will cut fuel delivery before the engine reaches its maximum RPM. The driver can press the pedal through the floor and nothing will happen past that point. The computer simply will not allow it. This brings up the turbo, because no conversation about diesel power is complete without it. A turbocharger uses the energy from the engine's exhaust gases, energy that would otherwise be wasted, to spin a compressor that forces more air into the cylinders. More air means more fuel can be burned, which means more power without increasing engine displacement. Turbos are why a 14-liter diesel making 500 horsepower exists in a package that fits under a hood. But turbos also have their own relationship with RPM. They are most effective within a specific range, and the engine is tuned to stay within that range. Push past it, and turbo efficiency drops. Exhaust temperatures climb, and the thermal load on the engine increases rapidly. The RPM ceiling protects the turbocharger just as much as it protects the pistons and bearings. There is also the question of what happens on a long downhill grade, which is where a lot of drivers and a lot of people watching trucks on the highway see something that seems to contradict everything said so far. You will sometimes see a truck hold its speed on a descent without the driver touching the brakes at all. That is engine braking, and it is one of the most important and least understood tools a professional driver has. When the throttle is closed and the truck is rolling downhill, the engine acts as a compressor, using the vehicle's momentum to push air through the cylinders against resistance. This creates drag on the drivetrain and slows the truck. Most modern semi-trucks also have an exhaust brake, or a Jake brake, a compression release brake that amplifies this effect dramatically by venting compressed air out of the cylinders at the top of the compression stroke, rather than allowing the air to push the piston back down. The result is a braking force strong enough to control an 80,000-pound truck on a steep grade without ever touching the service brakes. If you have heard that distinctive rattling machine gun sound from a truck on a downhill, that is the Jake brake working. And all of this happens well within that 2,100 RPM range. The reason this matters is that brake fade, the loss of braking effectiveness from overheated brake drums, is a serious and deadly hazard in trucking. Engine braking eliminates that risk on long descents by doing the work mechanically rather than thermally. Brakes are saved for emergencies. The engine handles the grade. One more thing worth mentioning, because it comes up every time someone starts talking about diesel revolutions per minute limits: the question of emissions. Modern diesel engines operate under strict EPA regulations that govern not just what comes out of the tailpipe, but how the combustion process itself is managed. Diesel exhaust fluid, particulate filters, selective catalytic reduction systems, all of these are integrated into the engine management strategy. And all of them have optimal operating ranges that align closely with the low revolutions per minute, high torque profile these engines already use. Running higher revolutions per minute does not just hurt fuel economy and durability, it pushes combustion temperatures and pressures into ranges where emissions control becomes significantly harder to manage. The revolutions per minute ceiling, in other words, is also partly an emissions compliance tool. Every system on a modern Class 8 truck, mechanical, electronic, chemical, is working in concert to keep that engine in the zone where it does everything right at once. So pull all of this together and you see something elegant hiding behind what looks like a simple number. The 2,100 revolutions per minute limit on a semi-truck diesel is the physical intersection of combustion chemistry, thermodynamic efficiency, mechanical durability, fuel economics, turbocharger physics, and driver safety. Raise that ceiling and you would get a hotter engine that wears faster, burns more fuel, runs its turbo outside its efficient range, and reaches an overhaul in 300,000 miles instead of 1,000,000. You would save 10 minutes on a cross-country run and spend 3 times as much keeping the truck on the road. The engineers who designed these engines understood something that is easy to miss when you are standing next to one of these machines watching it rumble at what sounds like barely above idle. Slow is not weak. In a diesel, slow is exactly where the strength lives. That low, heavy throb you hear from a loaded Peterbilt pulling onto the highway is not the sound of an engine holding back. It is the sound of an engine running exactly where it belongs, doing the most work at the least cost for as long as possible. And if this is the kind of thing you find yourself thinking about when a rig rolls past you on the interstate, you are in the right place. We have a full series of videos going deep on semi-trucks, how their transmissions work, why their brakes are built completely differently from anything on a passenger car, what actually happens inside a diesel engine during a cold start in January, and a lot more. It is all on this channel. Hit subscribe and you will not miss any of it.